Bismillahirrahmanirrahim. Today we will be talking about nanotechnology and solar energy. Actually, we have already completed the topics mentioned in the course outline of nanophysics and technology, but we have extended the course outline to some new topics that are of interest and are useful for the students. So therefore, in this today lecture, we will basically try to correlate the nanotechnology with solar energy, and we will discuss how the nanotechnology is used to harvest the solar energy and use the solar energy for renewable solar energy as a renewable energy source. So this is actually the part of our lecture series in the nanophysics and technology. So basically, in discussing the solar energy, we need to know the solar cells, and before discussing the solar cells, we need to know the solar spectrum. Actually, the solar spectrum contains 43 to 45% of the visible light and 3 to 5% of ultraviolet light. So we can easily utilize the visible light for different purposes. So normally, if there is a semiconductor material, normally if we look towards it an isolated atoms, if you want to, according to the Bohr theory, if you want to move the electron from one isolated energy level to from one energy level to another energy level, then the energy given to the photon should be at least equal to the difference between the energy levels. That means when an electron get an optical energy whose magnitude is equal to the difference between the energy levels, then the electron will be shifted from ground state to excited state. Similarly, if you want to move an electron from the valence band of a semiconductor to the conduction band, we need to provide an equivalent amount of energy, that is the band gap energy. So a photon from the sun generates an electron hole pair in a semiconductor. How it is created? The visible light photon looking toward the band gap of that particular semiconductor is absorbed, and as a result of this absorption, two charge pairs are created. One, an electron in the conduction band, migrated electron in the conduction band, and a hole in the valence band. So this charge pair is created, and that could be utilized for different purposes. So the electron is pulled to the front, the hole to the back of the solar cell, thereby creating a battery. So I mean, when these charge pairs or these charges are pulled by some means, or it is migrated to the surfaces, and then it can be utilized for charging the battery or for creating the battery, and that could be utilized for different energy purposes. So we have energy diagram of a solar cells. So if we have a solar photon, so what happen? The electron and hole are pulled apart by the electric field between the p and n type. If we have a semiconductor material that is actually made from the p-n junction diode, so what happen? There is a junction, and the solar energy photon, the solar photons, I mean the optical photon, that is absorbed when its energy is equal to the band gap energy. So what happen? An electron is migrated to the valence conduction band, and a hole is created in the valence band. So the electron and hole are pulled apart by the electric field between the p and n doped region. So it is both the charges which are created that are pulled, and as a result of this migration of charges, we create a current. So it is critical not to lose electron and hole on their ways out. Crystalline semiconductors are good at that, but expensive. So a question, in some cases, the other possibility in parallel to the electron hole pair creation is the electron hole pair recombination, where the electron recombine with the hole and emitting the extra energy in the form of light, or depending on the band gap. So I mean, that energy is created there. So in this slide basically we want to in the first picture the capture of photon is shown. I mean the photon is captured, that lead to the creation of electron hole pairs, and as a result of the electric field between p and n dope regions, these charges are separated, and further these charges are collected at the ends, which could be utilized for different purposes. So electron hole pairs, electron holes and exciton are basically also the theme of this slide. How the electron are created, this slide basically shows here is a band gap. If we consider a pure semiconductor material, then at 0K its valence band is completely filled, whilst conduction band is completely empty. That is why an intrinsic semiconductor is working as an insulator at 0K. But as far as its temperature is increased, or even the semiconductor at room temperature, some of the electron in the valence band get enough thermal energy to be migrated to the conduction band, leaving behind a hole. So that is why we have readily available charges at the valence band and the conduction band, and when the electric field is applied, so that charges could be utilized for the current. So a photon excites an electron across the band gap of a semiconductor. So what happens? That leaves a hole among the occupied levels in the valence band and an electron among the unoccupied levels in the conduction band. So electron and holes are attracted electrically and can form an exciton. This is actually the most important sentence, that electron and holes are attracted electrically and that form an exciton similar to a hydrogen atom. In organic semiconductor, it takes a significant amount of energy to break them apart into free carriers. So creation of electric field at p-n junction. How the electric field is created at the p-n junction? So the donors are field impurity level just below the conduction band minimum, and it can be easily donate electron into the conduction band and produce n-type conductivity, that is negative charge carriers. Acceptors are actually empty impurity levels just above the valence band maximum, and it easily accept electron from the valence band and produce p-type conductivity, that is actually the positive carrier. So actually this two diagram shows the electron flow downhill from n to p-type until the Fermi level line up. This is the case. And in the second figure shows the depletion of Fermi level mind gap. So here we can see how these electrons or these charges are migrated when both n-type and p-type materials are brought in contact to each other, so creating the forbidden regions. So this is the separated, initially the separated n and p-type semiconductor materials are shown, and finally after forming the p-n junction, the depletion region is shown, which is created due to the transfer of charges. And depletion region is actually depleted from the carrier because the positive and negative charges mix with each other and forbids the further and develop a potential, and this potential forbids further mixing of the electron and hole with each other. So application of the p-n junction, it is used in solar cells and even in the light emitting diode. Here we can see that a photon create electron hole pair, and that could be utilized for different purposes. And similarly in light emitting diode, the electron hole pair recombine into photon, and we can get very interesting light from the light emitting diode. So this is actually the opposite process. In one case photon create electron hole pair, while in another case electron hole pair, when it recombine, it create photon and we produce light out of that. This is a really interesting image that shows the type of the supercell and its corresponding efficiency. Basically is really very broad understanding of the different company that are producing different sort of solar cells, and their corresponding efficiency is shown. And the vertical sides we have the efficiency, while in the horizontal sides we have the year-wise improvement in the efficiency. It is very clear from the figure that with the advancement in age, the efficiency of the these solar cells interestingly increases, and we are getting some solar cell whose efficiency is around 40.7%. so that is actually the gradual increase in the efficiency, because people are looking towards the useful utilization of the electron hole pair and their migration to the reactive sites. This is a book that is basically gives a research based understanding that how we can utilize the solar energy for different purposes. So solar cells containing nanoparticle and that could be synthesized by a dye molecule similar to that at the core. I mean, in some cases we have semiconductor mixing, in that is also utilized for solar cells, while in some cases we have dye synthesizing. In dye synthesizing, a particular dye is used to synthesize the semiconductor and reduces band gap or create some levels in the band gap of that semiconductor material, shifting the absorption rate of that semiconductor material and leading to the improved absorption efficiency, thereby increasing the efficiency of the solar cells. So especially it is used for TiO2, just like for TiO2 nanoparticles act as acceptor collecting electron, so the electrolyte act as a donor collecting the holes. So we have ruthenium dye molecule for some particular crystal cells. This is actually the molecule, and that absorb more than 90% of the sunlight, and that could be used for that particular purpose. So the dyes are made with ruthenium, an expensive for the transition metal. So how we can, is it possible that we can use iron instead of ruthenium? But many questions arise instead of that, because we have some complication in the structure of that. The energy level diagram clearly depicts the different energy levels between HOMO and LOMO. HOMO is actually highest occupied molecular orbital, while LOMO is the lowest unoccupied molecular orbitals. So how the electrons are moved, or it make transition between HOMO and LOMO, and how these states are created due to the dyes, or due to acceptors, or due to donor, modifying the band structure of that particular material, a semiconductor material, or maybe particular dye, or particular some other material. So that is why leading shifting the absorption edge. So here we can see the photon is absorbed, and as a result of the dye, and the photon is that lead to the transition of electron from the HOMO toward the LOMO, and that further comes, and that is collected at the negative contact potential, and the other photon, the other positive charge, or what you call is the deficiency of electron, that is actually the hole that is collected at the positive terminal of the battery. So that could be utilized. So we have generic molecular cells as well, that is also use the same process of HOMO. So instead of the holes going uphill, electrons going downhill to fill the holes. So that is also the other process in which the current is created, and that potential difference is utilized. We have efficiency limit for the semiconductor. If we have semiconductor solar cells, so its efficiency is 30% for a single junction, that is and it is around 70% for multiple junctions if we utilize it in multiple junctions. And if we use molecules, then for it is 20% for a dye synthesized solar cells that have a single junction. That is a basic thing. So I mean, this is a bit interesting how we can use a different sort of materials to improve the efficiency of that particular semiconductor materials. So we have the basic spectroscopy of the HOMO and LOMO of that are actually the donor and acceptor orbitals of that. So that could be obtained from the X-ray absorption spectroscopy and from the photoelectron spectroscopy, where the binding energy is shown. Here the N1 is absorption spectra is shown, and the different peaks are characterized, showing the different peaks are due to the transition of electron between the different energy levels, and that is described here in both cases. We have the transition at metal center of a dye molecule as well. That is specifically used for X-ray absorption in element selective cases, that is especially for Fe2P core levels, that detects the oxidation state, speed state, and some other and the legend electric field. So that is also a way how we can create or we can characterize the peak that are created. This is the X-ray absorption spectra of a solvent Fe complex for the low spin ground state and high spin excited state of the electrons. So we can see that the curve is drawn between the energy and normalized absorption, and the low spin and excited high spin curves are really interesting, and that are opposite to each other in this specialized curve. So we have spin excitation in 100 picosecond, that is shown here, and atomic motion in 100 fm/s, and further electronic motion in 1 fm/s is also described. If we have nanostructure solar cells, so what will be the efficiency of the nanostructure cell and how the electron hole pairs will be created. So in this case, incident light create exciton electron hole pairs, and in the second steps hole diffuse towards electrode, and third step holes trapped in an isolated island of organic molecule, and finally electron are moving towards the electrode. So both electron and holes are collected and thereby creating the current. In this case, this nanostructure solar cell. So it is a better design of regular array of nanorods, how to improve the efficiency of this particular solar cells. So using the nanostructure factor structure to minimize the path of exciton electron holes to the nearest electrode, and that avoid the losses, thereby improving the efficiency. This is some of the images, SEM images from the growth time in for different material, in which it is clarified that the growth time increases from left to right for different resolution. Here we can see at A the growth time. We are looking toward the growth in increasing the changing the properties of the the synthesis, and the changing the root or parameter of the synthesis. We can change the growth time of that, and this is basically for Z and O nanorods that are used for electrodes. We have nanorods coated with the nanocrystal as well, that are regularly arranged, and that is actually a type of quantum dots, just like for CDSE, that are attached to a nanowire. And this is basically a sketch of that arrangement, where we have silicon SNO2 or glass at this portion through which the light is absorbed, and we have SNO2 or glass at the upper portion as well. And as a result of this, the liquid electrolyte or whole conductor are present inside. So CASSE nanodots that are in the nanostructure in 3 nanometer replace the dye, and absorption spectrum is tuned by the size of the dot, and that basically describe that. We have polymer solar cells as well that are also utilized for converting the solar energy into electrical energy. In case of polymer chain with the diffusing polaron, that are actually electron plus distorted polymer surrounded by fluorines molecule as acceptor. So the fluorines can accept up to 6 electrons in its LOMO for this particular purpose. So we have fuel from the sun in different purposes, just like what the trees are using their photosynthesis, that are also utilizing the solar energy. We have biofuels to convert the biogas into the biomaterials, I mean into gas and fuels as well. We can split water to convert the water into hydrogen, oxygen, and hydrogen can be used as a source of energy as a fuel. And we have fuel cells as well creating electricity directly from fuel and oxygen. How it works, if we consider for the photosynthesis, I mean the plant converts solar energy into chemical energy that is utilized, and less than 20% of the solar energy get converted, but the initial part of the conversion is very efficient. So this is oxygen evolving complex in this particular case. So this is something about the conversion of the solar energy into electrical energy, and the way how we can utilize this particular nanotechnology for different purposes are utilizing the solar energy. So this is something of today's lecture. Thank you very much.